All right, so in this section, we are going to utilize the average switch model we have derived previously to evaluate the energy conversion process of the switch network. So again, we use the SEPIC topology as an example. So we introduce the concept of the indirect power here. So I will first plot the schematic of the SEPIC topology by decoupling the time environment network with the switch network. So here is the time environment network. So here is L1, L2, C1, C2, R. Input port is denoted as the DC quantity plus small signal AC. This is the input port current as the IL1 plus small signal IL1. And this is the inductor current of the L2, so IL2 plus IL2 cap. And here is the voltage V, capital V, C1 plus small signal DC1. So the direction of this current goes to up. And here is the capacitor voltage VC2. Okay, so the rest part is the switch network part. So the MOSFET is here, right? We extract it. And diode is here, we also extract it. So here is going to the two-port network. For this SEPIC topology, we mark the polarity of the port voltage as V1. So port 1. V1 is positive on top. And the port 2. So for port 2, due to the feature of the SEPIC, we mark the positive on bottom. So this is the port 2 current, and this is port 1 current. Because we mark the polarity of the positive on downside, so inside this two-port network, we would have the coupling point inverted, right? So inside this is going to be the linearized model we have just derived using the independent sources and transformer, right? So here is the plus minus. So here is opposite. And we have a current source here. So the voltage source is denoted as V1 over dd prime times controlling signal D cap. And this independent current source is also controlled by D. So the value here is I2 over dd prime D cap. So that's the SEPIC linearized model, right? SEPIC linearized model. Then we introduce a definition here. So the transformer here is the virtual transformer. So we mark the wave line and the dash line to indicate that this is a virtual DC plus AC transformer. So next we introduce the definition. So we decompose those two-port network electrical signals to be two parts. For example, V1 is decomposed into the average over one switching period of V1 plus V1 wave. And for the I1, we do the similar thing. It is decomposed into two parts, I1 average plus I1 wave. So on the right-hand side, we can see that we have two parts, right? So first part is the average part. This is exactly the DC average components. And second part is the waveline part. So those are the AC switching components. So for those AC switching components, if we do the average over one switching period at steady state, they should be equal to 0. And based on those features, we can later on plot its waveforms correspondingly. And similarly, for the output port, port 2, we can also write those group of formulas. So we have the output port voltage, V2, equals to the average of V2 plus AC switching components of V2, right? And for the port 2 current, okay, also two parts. So similar to this one, the average of V2 wave equals to 0, and the average I2 wave equals to 0. So then we can plot the profile of those V1 wave, I1 wave, V2 wave, and I2 wave correspondingly for SEPIC example. So in SEPIC, so we construct the group of 4 waveforms. First one, we consider the V1 wave. In time domain of V1. So there are two operation modes at steady state. So here is the DTS, here's TS. So because the average of V1 wave equals to 0, and meanwhile, for the V1 port, right, when the switch is on in mode 1, so the DC voltage, right, DC voltage in mode 1 should be equal to 0. Therefore, the AC switching components for mode 1 should be equals to minus, right? So this quantity equals to 0. So therefore, in mode 1, V1 wave should be equals to negative V1 average. So the level here is denoted as minus. And for mode 2, starting from DTS to TS, because the average of V1 wave over one switching period equals to 0. And in mode 1, the level here equals to minus V1 average, so that we can calculate or derive the level in mode 2 should be equal to d over d prime times this level. So d over d prime. You will see that this will ensure that this relationship is fulfilled, right? Fulfilled. And then it's going to be repeating over the switching cycles. And next, let's look at the waveform of V2 wave. For V2, it also contains two segments, right? Two segments from DTS to TS. For V2, in mode 2, the V2 voltage will be equal to 0 because the diode is conducting. We consider the diode is ideal, so the voltage equals to 0. If in mode 2, the voltage V2 equals 0, then we will see that the V2 wave will equals to minus V2 average. So the level here will be equal to minus V2 average. And again, we also have that the V2 average equals to 0 over one switching period, so that we can make up or compensate or calculate the level here. Level here should be d over d prime times d prime over d times the level here, right? So that's the profile for V2 wave. And next, let's look at the current I1 wave. So for I1, when the switch or MOSFET is off, right? When the MOSFET is off, the I1 will be equals to 0 in mode 2, right? So if you equal this to 0, you will see that in mode 2, the I1 wave, right? I1 wave will be equals to minus I1 average. So the level here will be, in mode 2, will be minus I1 average over one switch period. So the correspondingly, because I1 wave average equals to 0, so we can derive the level here. Right? Level here will be equals to d over d prime over d. Okay, that's for I1 wave. Last one is going to be I2 wave. We also have that, the I2 wave average equals to 0. So correspondingly, we can plot so for I2, in mode 1, when the diode is off, I2 equals to 0, right? So if I2 equals 0, then the I2 wave will be equals to minus I2 average. So level here will be equals to minus I2 average. And same, right? Due to this phenomena, the average of this I1, I2 wave equals to 0. So therefore, we can calculate that the level here will be equals to d over d prime okay, so that's the complete profile of the 4 set of waveforms for the extracted switch network. Okay, we have erased the blackboard and keeping the typical waveforms of the V1, V2, I1, I2 wave line. Okay, so now let's try to analyze the power flow of the port 1 and port 2. So first, let's look at the power flowing of port 1. So we know that the power equals to the product of voltage and current. So for the input port, port 1, P1 will be equals to the product of the port 1 voltage, which include 2 ports, right? The V1 average plus V1 wave. And the port 1 current also contains 2 ports, the I1 average plus I1 wave. Then we can decompose this product, so which will be equal to 4 parts, right? Plus V1 average times I1 wave plus I1 average times V1 wave plus the product of V1 wave and I1 wave. So we can introduce the concept of net power flow. So we denote as P, capital P1. So the net power flow will be equal to the, this is lower power, right? Instant power, equals to the instant power average over one switching period. So if we assume that the switch is ideal, we do not consider the conduction loss and the switching loss of the MOSFET, then the net power flow for the MOSFET should be equal to 0. So P1. So if we assume ideal switch without considering any internal power losses of the MOSFET, then the net power flow, capital P1, should be equal to 0, right? So it means that the average of the instant power over one switching period equals to 0. On the left-hand side, we put the average P1. And on the right-hand side will be the average of this port, right? So this part contains four components, right? So if you look at the middle two, right? So we do the average over one switching period. So the middle two will contains a part which is the average of I1 wave. So this is wave line. And V1 wave. We previously learned that the average of I1 wave over one switching period equals to 0. And V1 wave equals to 0. Therefore, if we break the brackets and decompose it into 4 parts, the middle two will be eliminated, equals to 0. So the equation can be replaced by left hand side is 0, right? 0 watt. Right hand side only we have 2 parts left. So therefore, we can find out that this product equals to minus this product. So we basically, if we observe this resulting formula, we can assign physical meanings to it. So on the left-hand side, if you look at the left-hand side, this is the product of the average voltage and the average current going into port 1. So this is meaning the DC power flowing into port 1. And on the right-hand side, so this is the average of the product, right? So V1 wave, I1 wave is the AC switching component of the signal. So the product will be the instant AC power, right? And average means the AC average power flowing out of the port 1. AC average power flowing out of port 1. So this tells us that we kind of convert the DC power into a AC power, right? So this means that the transistor or the MOSFET here behaves like an inverter. Behaves like an inverter. And similarly, we can also do this analysis for power flowing of port 2. So the procedure is pretty standard, right? Pretty standard. It's kind of, we just replace the letter subscript 1 by 2. We do exactly the same thing. So we can calculate the net power flow of the port 2. P2 equals to P2 average. And also, we assume that the switch for port 2, which is the delta, if we assume the delta is ideal, the P2 will be equal to 0. The net power flow out of port 2 equals to 0, right? Then we can do the same thing. Only difference is replace 1 by 2. So we will derive the similar results, right? So we will have the similar results. The only difference is that the subscript 1 is replaced by 2. So here I'd like to write the results directly. So minus the product of V2 wave and I2 wave equals to the product of the V2 average So if we observe at the result here, right, this contains two parts. Left-hand side is the similar as what we put here. This is the AC power flow, right? So AC average power flow into port 2. And here, this is the DC power flow out of port 2. So we would see that for the port 2 is kind of it converts the AC power into a DC power, right? So basically we will say that this is the for the port 2, the switching diode, right? Switching diode behaves like a rectifier, right? Rectifier. So rectifier means that it converts the AC power into the DC power. So to summarize, we can see that this switching network does the task of indirect power flow. Right? Indirect power flow means that the input port is first converts the DC power into a AC power, and on the output port, it converts the AC power into the DC power. So it's like a inversion and a rectification process. Okay. So in this section, we have studied the energy conversion process of the indirect power conversion for the switch network. So we can know that we can try to reduce the duration of circuit operating in indirect power flow state. So by doing this, we can reduce the power loss of the conversion circuit.